Okay, so today we have Nat Tantivasadakarn from Stony Brook University giving us a tensor network perspective on dualities and non-invertible symmetries.
Yes, so thank you for the invitation to give it. I don't need to be mic'd. So. Okay, yeah.
Your room is mic'd.
So thank you for the invitation to be here. It's great to meet people, visit here again. So today I'm going to be talking about dualities and non-invertible symmetries, and I'm going to try to present that through a tensor network perspective. And this work is in collaboration with Stony, who was here at some point, and Shuhang on this paper. And also a more recent paper I did in collaboration with Dachon and Arco. The central topic I want to talk about today is duality. And just to sort of step back, a broad definition one might take of a duality is viewing the same system at a different angle and in such a way that it might offer insights into its properties. So you might have a description A of your system, and maybe through a duality transformation, you can describe it in a totally different way, description B. And maybe you might think that studying circles are easier than studying squares, so we might as well do the duality transformation and studying it in the way that fits us most. So for that description, it allows us to gain insights for description A, which might be a bit harder. So today I want to talk about duality in quantum many-body systems. But first of all, let me just step back first to maybe give some intuition for duality in quantum mechanics. And so what I want to do today is I just want to spend some time on what is a duality in quantum mechanics, and then goes to duality in a quantum many-body system. And the example that I'll focus today is the so-called Kramers Wannier duality in the transverse-field Ising model. And then I would like to talk about how we can reformulate that using the language of tensor networks, and how tensor network is a very natural language to describe these dualities on the lattice. And then beyond that, I'll try to motivate how we can study some self-dualities beyond the Ising model, but in some sort of simple generalization of the Ising model. Okay, so that's what I plan to do today. So what is a duality? So maybe in quantum mechanics, we can think of, so what do we mean by viewing the same system in a different description, but it still offers the same information? So one example you might be very familiar with is, for example, maybe you have a lattice in real space, right? And you can go to momentum space and via the Fourier transform, and whether you describe it using X or P, right? It offers the same information, even though this one is a discrete lattice, right? And this is a continuum. Maybe if you work in quantum information, you might be more familiar with the block sphere, where you can either write your qubit in the computational basis, the Z basis, or in the X basis. And again, they're sort of related by this Hadamard transformation, which you can think of as a Z2 version of the Fourier transform. It's very simple in this case. Now, in addition to duality, one might want to impose more information, such as a self-duality. And in this example above, going from the lattice to the Brillouin zone is not self-dual, right? Because both sides of description look a bit different. But there are examples where when you do the Fourier transform, they're self-dual. For example, when you're on the real line, right? If you are on the real line and you go to momentum space, that looks the same. And also in the Z2 case, when you do the Fourier transform, it doesn't matter whether it's X or Z. It looks exactly the same. It's just like you sort of rotated your picture a bit. So it's sort of interesting to study, well, when do you have a self-duality? And in particular, if you have a self-duality, that can even become a symmetry of your system. So let me give it a simple example. Let's just consider the harmonic oscillator, right? The quantum harmonic oscillator. And the Hamiltonian is p squared plus x squared. Now, if you write down the Hamiltonian and its eigenstates, right, it is invariant under performing this Fourier transform and then relabeling E and X. So for example, the ground state is just this Gaussian, right? If you perform the Fourier transform, you have momentum space. The ground state is still roughly a Gaussian. And so if you relabel P and X, right, it maps back to the same, back to itself again. So you can say that this Hamiltonian has a self-duality, which becomes a symmetry, which is given by roughly swapping P and X. So this is the quantum mechanics version of a duality. Let us now see what happens in the many-body version. So what is the many-body version of duality? And I'm now going to talk about, we're going to go now from 0 plus 1D to 1 plus 1D, which is the Kramers Wannier duality. So in quantum mechanics, we say we can map between description A and description B, right? But now what is the many-body version? Instead of description A and description B, one might say we are viewing the same system as a different phase of matter. Maybe I have a phase of matter A and I have a phase of matter B, and they're related by this duality transformation. Now you might object that what does it even mean to equate two phases of matter together, right? They might not, for example, not even have the same partition function. Maybe they have different ground state degeneracy on certain manifolds, right? So in what sense are they dual? So in what sense do these two phases of matter contain the same information? I'm going to address that in a bit. But let me just pose that there might be some information for phase of matter A and phase of matter B in which they carry the same information. And what's interesting is we can now ask a similar question, when can we have a self-duality? In particular, suppose I have a Hamiltonian phase of matter A, a Hamiltonian phase of matter B, and suppose I have some parameter to tune between the two. You could have an interesting scenario where when you tune between the two, you can actually swap them. So you can tune through some parameter, right? And at the end of the day, what you thought was phase of matter A became phase of matter B and vice versa. So that's what we're interested in saying. And by the way, I didn't think I had to say this, but actually this picture, this is not AI. Like 2 years ago, I wouldn't have to say this, but I had to make it clear. So it's a very interesting optical illusion. You should go check it out on YouTube. But yes, this is an actual thing. Okay. So this will come into the context of the transverse-field Ising model as follows. Let's consider this Hamiltonian, where there are two competing terms. One is a transverse field term, which tries to pin all the spins in the plus direction, so they all point to the right. And the other one tries to align them together, so you get a transition between a ferromagnetic phase and a paramagnetic phase. And then there exists a so-called duality, which roughly swaps the roles of z, z, and x, in which once you swap them and rescale the Hamiltonian by h, you find that what was the ferromagnet became the paramagnet, and what was the paramagnet became the ferromagnet. So it is sort of like this picture where on one side we have the ferromagnet, one side we have the paramagnet. They're related by this duality. You can tune it all the way to a critical point where actually once you tune that, both of the sides actually look the same. And once you get to the other side, the paramagnet and the ferromagnet are swapped. So the interesting thing where we want to study here is actually at the critical point, right? This duality actually does not look the same in each side, but once you tune to the critical point, now the two sides look the same. So you get an extra symmetry. So we want to study what is this extra symmetry we gain when we tune to the critical point. So there is some operator. I'll need to clarify what I mean by this operator. But it becomes a self-duality at a critical point, and we want to study it as a symmetry. Now, of course, this sort of property was pointed out, almost 80 years ago by Kramers and Wannier. They said that this is in the context of the analogous classical stat-mech model in 2 plus 0D. And they say that there is a sort of symmetry property which relates this ferromagnetic and paramagnetic phase. But they said it has a symmetry property because, well, they didn't really know in what sense it was a symmetry. And now here, let's try to make it more precise. So what is this Kramers-Wannier duality a duality of? I mentioned that this duality is swapping z, z, and x. And the intuition, roughly, is that x is what detects a charge in this Ising model, because our global symmetry is a spin flip, right, which is the product of all x's. If you detect locally x equals -1, it means that you have a z2 charge in your system. And under this duality, we're mapping x to zz, and zz is detecting whether the domain walls are aligned or not, right? If zz is equal to 1, it means the spins are aligned. And when you have zz equals -1, it means you flip one of the spins down, so that's a domain wall. So roughly what Kramers Wannier is trying to tell you is that you're mapping between the charge variables to the domain wall variables. Okay, so naively you would say, okay, so Kramers Wannier is a duality between these charge and domain walls. Oh, good. But there's a subtlety, which is there can only be an even number of domain walls, right? If you flip a spin, you always create domain walls in pairs. And that comes from the fact that if you product over zz, right, this telescopically cancels and you get +1. So it means that you can only have an even number of domain walls, but on this side, you can have either odd charge or even charge. So it means that the duality only holds in the subspace where the product of x is equal to +1, right? That means that's in the even sector of the model, or like the singlet sector.
You're in periodic boundary.
Yes, yes. So this is periodic, right? So you can choose either periodic or anti-periodic, but the duality only holds in one of those sectors. So you cannot make a claim about every sector at the same time. You're sort of stuck saying when this is periodic, you can map to the even sector, for example.
But it's a problem of the boundaries, right? It's just that in the interior you can always do the
Right. It's
so the boundary you're frustrated. If you
Yes,
do,
yeah.
you do periodic
when you close it up, yeah, that's the problem. And you end up having to do this projection where you have to project into the subspace where you're in the even sector. Okay, so the many body version of duality is a bit more subtle because it's not a duality in the full Hilbert space. You have to restrict to a subspace. So what we say, we have this critical Ising Hamiltonian right at this critical value. We can say that, well, we can ask, is there a unitary operator that swaps x and z, that exchange x and zz? And the answer is no, because just this is an easy way to show it. If you can map x to zz unitarily, right, then you would have mapped this product of x equal to 1, right? So in the full Hilbert space, there's no unitary operator that does that. It's only unitary in the subspace where the product of x equal to 1. But we can compromise that a bit. It turns out that there still is a non-unitary operator which commutes with the Hamiltonian and does the job. So instead of conjugating my operator x by this non-unitary operator d, this d has no inverse anymore. What I'm going to say is I'm going to push x through to the other side of d, and there is an operator for which x pushes through and becomes zz on the other side. And I'm going to show you using pictures how we can draw such an operator diagrammatically.
I thought there should be some translation in the last village.
Yes, that's why you're very acute here. So that's why I secretly put this dagger here to get rid of the translation. So d actually, so in the continuum, right, on the lattice, if I take d times d and d, there will be a translation. That's why I put a dagger there to hide that, in case no one noticed that you did. So
in the continuum, d is equal to d bar.
Yes, but on the lattice, d
is
not. Yes, and it's because it's hiding that so d dagger is to d times translation.
And on the lattice, d is infinite order because of the translation.
Yes. Well, infinite order. It's not even invertible to begin with, but yeah, up to that projection. Yeah. Right. So if you do the duality, so in the full Hilbert space, if you do the duality and do the dagger of that to come back, right, you end up projecting something away. And you end up with this projection over here. So in the full Hilbert space, you do have a symmetry, a non-unitary operator which commutes with the Hamiltonian, but it does not have an inverse. And so we call this a non-invertible symmetry. And that's related to the fact you can sort of think of that as the analog of having, for example, you have a spin 1/2, tensor spin 1/2, there's more than one outcome, right? You might either project into the singlet or the triplet. And that's sort of this analogy here. It's not just one anymore. There are two outcomes. So this is sort of a primer, very baby version of non-invertible symmetry. And that's if you are in the full Hilbert space, you're forced to have this non-invertible symmetry. So duality, for self-duality symmetries, you can actually use them to realize non-invertible symmetry in quantum many-body systems.
Could you explain the comment about continuum and lattice difference?
Yes, it's a good point.
So that
So in the continuum, there is, so on the lattice, if you take D dagger, it's actually related to D times lattice translation in this case. And you might wonder whether you can get rid of it. And it turns out on the lattice you cannot. But when you match it into the continuum, this lattice translation actually acts trivially, and then you don't see it. So it's an actually very interesting point where when we try to classify symmetries in the continuum and try to match them with the lattice, actually they don't match. In there are cases where they don't match perfectly. And we know now examples where it can either be sort of two things mapped to the same symmetry, or one thing maps to two different symmetries in the continuum. It's neither injective nor surjective. So actually symmetries on the lattice, we need to sort of study independently. We cannot just use the classification of continuum symmetries.
Thank you.
Okay. So what I want to pose today is that was the example for the Ising model, where we have the Kramers Wannier duality, which describes the duality between the ferromagnetic and the paramagnetic phases in a spin chain with a Z2 symmetry. Now, of course, you can ask, how can we generalize this? And it turns out for cyclic groups or abelian groups, it's not too hard to generalize. People have done that. And that comes in the form of the clock and the Potts model. So you can also write similar models with the N symmetry, for example, which are self-dual. But it turns out that one can ask, if you go to a non-abelian group, can you get a self-duality? And it's similar to this Fourier transform I showed you earlier, where you have the lattice and the Brillouin zone, right? They're not. It turns out that for a non-abelian group, once you do this Fourier transform, you don't come back to yourself. So you actually cannot get a self-duality. So lattice, currently people only know lattice models for which it has a abelian symmetry.
Can you imagine a lattice model that has both G and rep G symmetry simultaneously though? So
Oh yes, that would be one generalization. Yes.
then you can do self-dual.
Yes, so that would be one example. And it actually would be encompassed in what I'm going to try to talk about here. So it turns out that in order to get these, get a self-dual model, we have to move beyond groups. And the natural language turns out to be something called self-dual Hopf algebras. I'm going to explain a bit why this is a natural generalization of this, but it allows, we need to go beyond groups. And what we construct is a lattice model in a tensor product Hilbert space, which we sort of call the Hopf-Ising model. It has similar ZZ terms and X terms, and they get permuted under a duality. And when you choose your Hopf algebra to be self-dual, you get this self-duality as a symmetry. So that's what I'm going to try to get to today. So although this model is a bit ugly, it's somewhat of a beast. Maybe I'll show you some of its beauty later, hopefully, by the end of the talk. Okay. So the general idea for getting non-invertible symmetries that I want to talk about today is, so recall for the abelian case, right? We know that we can perform this abelian symmetry, do a duality, and get back a dual abelian symmetry. So we get back to the same model with the same symmetry, and that's why we can get a larger duality here, which becomes a non-invertible symmetry. On the other hand, for this non-abelian group, what happens is you start with some non-abelian symmetry, you do the duality transformation, you get this non-invertible symmetry, and it doesn't look the same, so you don't get any extra symmetry. But what I'm going to try to do here, using going beyond groups, is that combining these two together, you can still have a non-invertible symmetry. When you do the duality, you get a dual non-invertible symmetry, and then this gets enlarged to an even bigger non-invertible symmetry. And the lattice model I'm going to construct is going to be using this thing in the middle over here. Okay. So hopefully I motivated you about why dualities are interesting and what we want to construct and generalize. And now I'm going to talk about the tensor network aspect of this. Let me just pause. Is there a question? Okay, so then let's talk about viewing this Kramers-Wannier duality as a tensor network. So what are tensor networks? Tensor networks, you can sort of think of them as they're different. These different dots here are tensors, and each leg of it is the number of ranks of your tensor. So, for example, a thing with one leg pointing out is a vector, two of them is a matrix, right, and so on and so forth. You can glue these together by tensor contraction, and you can build quantum many-body states and quantum many-body operators using this. And so it is a very nice ansatz for us to build these operators that we would like to study. And I'm not going to go into the full sort of formulation of tensor networks. Instead, I'm going to be using a very specific building block. We'll be using very specific tensors and trying to build our way through. And that actually comes in the form, it's known in quantum information as something called ZX calculus. And it's actually very kid-friendly. There is even a book you can read to your kids. This says, "Hi, I'm a spider." I have this book in my office, and it's quite pedagogical. So you could hopefully it'll be very friendly. But let me just set the stage for what tensors we want to use. The idea is very simple. I'm just going to have something called a green-looking tensor and a red-looking tensor. The green one here is just a GHZ state. So it's all 0 or plus all 1, as for example, as a 3-leg tensor. You can also think of it, suppose time is going up. If I have one input leg and two output legs, you can think of this as a copy tensor, because if I input 0, I'm going to get 0 and 0. And if I input 1, I'm going to get 1 and 1. So this tensor is just copying stuff for me. And you can call this, well, people call this a green spider. You can call it copy tensor. You can think of it just as a GHZ. And since there are two colors, you might, and the mnemonic I use is green is for GHZ. Okay. And now red is just the Fourier transform, or the Hadamard version of this. So instead of all 0 plus all 1, I have all plus plus all minus. Now it turns out if I expand this in the 0-1 basis, you can convince yourself that what this does is actually it's summing two things. So if I input j and k, the output here will be j plus k. So it's a sum tensor. And these tensors have very nice identities. They interact very nicely with the Pauli operators. For example, we know this is the GHZ state. So it's invariant under flipping all the spins. So if I apply x on all the legs, it does nothing to my tensor. Also, it's the ground state of the Ising model, right? So if I add z on 2 legs, it's also not going to do anything. And it doesn't matter which 2 legs you add. For the Hadamard version, it's just z and x are swapped. So z on all legs does nothing, and x on 2 legs does nothing. Okay, far so good. And these two doesn't need to be 3 legs, can be right, and they're connected by the Hadamard, which I'm going to label with this yellow box. So yellow box is Hadamard. If you apply it on every leg, it's going to change the red to the green. And now I don't need to have just 3 legs. They're going to have as many legs as I want. And a key property I'll use here is called fusion, which is, well, if I have a GHZ state, another GHZ state, I contract them together. It's just a bigger GHZ state. It's just a bigger ferromagnet. So it just becomes a bigger, tensor with the same number of legs pointing out. Okay. So that's all the building blocks I will use. And I'm going to use this to create the Kramers-Wannier duality. So one nice application, the reason why people like to think about this in quantum information is that you can deform these diagrams arbitrarily. So you can think of it topologically without changing the linear map it represents. So for example, there's one quantum gate that people like to use in quantum information. It's called xenon. And it's basically taking this green tensor and connecting it with this red tensor. So what does it do? If I have A and B, this green is going to copy my state A into 2, and then this one is going to sum it together. So if I input A and B, what you realize at the end is that A stays A, but the result of A gets added mod 2 into B here. So this is called the control not gated quantum information. But it turns out that whether you write it this way or this way or this way, it realizes the same linear map. So you can deform this arbitrarily. And then there are extra rules, which I won't go into the details, which you can use to manipulate and these diagrams. And you can show that one linear map is equivalent to another linear map just by these manipulations. Now, before I talk about this Kramers Wannier duality, I just want to make, this is probably the most technical slide in this talk. I'm going to make a very nitpicky point about there are actually 2 Ising models. One I'm going to call Z2 Ising model, which is the one we already discussed. The other one is called, I'm going to call it the rep Z2 Ising model, where I just change Z with X. And the reason I'm being nitpicky about it is because they have different symmetries. One is called a Z2 symmetry. And what a Z2 symmetry does, it acts by flipping spins. And so that's represented by poly X. Whereas the rep Z2 symmetry, rep Z2 is actually the representations of the Z2 group. And there are 2 irreps. One is the trivial irrep and one is the sign irrep. And the sign irrep acts non-trivially on state 1. And so that acts like a poly Z. And so in the abelian case, these are actually related by the Fourier transform. In the non-abelian case, they become distinct. So that's why I just want to nitpick about this point here. What we're going to do is we're going to first relate this Ising model to this rep Z2 Ising model via the duality transformation, which I'm going to explain in a bit. And this will generalize to the more general case later. That's why I want to make this one. Okay. So now I'm going to talk about how we realize this duality. And then there is a very closely related concept, which is gauging. So when we think about gauging, we have a global symmetry, right? And we want to promote it to a local symmetry action, such that at the end of the day, we impose some Gauss law, right? And this symmetry is enforced. We go to this gauge invariant subspace, the symmetry is enforced. Now it turns out that, let me just take these green, this GHZ states, and just glue them with the red one in this manner. And what happens is you can check that the Z2 symmetry, if I act by this splint flip, which is X on every side, it gets totally absorbed into this map. So it means that whether I act with the X or not, it does not matter. So one way to check that is you can use these identities, which is saying, suppose I act with X in the bottom here, you can push it up to X on the left and on the right, and then these 2 X's sort of cancel on this red tensor. So the Z2 symmetry, you can say this symmetry has been gauged by this map. So this map is what performs the gauging. On the other hand, I have my dual symmetry, which is the rep Z2 symmetry, which is presented by Z. And because I just need to swap green and red and X and Z, right? You can similarly convince yourself that if I have Z on the top and I push it down, it's going to be gone. So this is a map relating a system with a Z2 symmetry with a system with a dual rep Z2 symmetry on the other side. And this we can associate to gauging. To make the relation to gauging even more clear, what we can actually do is actually perform the gauging procedure. So you can use these ZX diagrams to deform this into this picture. So let me explain what this picture is, and then I'll show you that it's equivalent to this. So what I'm doing here is the following. So if I have, for example, a system with Z2 symmetry, you can think of them as, I have matter degrees of freedom. What we usually think of is we add our gauge fields. Let's say that my 1D lattice, I have my matter degrees of freedom on the vertices. I introduce gauge degrees of freedom on the edges, right? Initialize in a certain state. In this case, it's in the 0 state. So I add the gauge fields. Then what I'm going to do is I'm going to project into the gauge invariant subspace. One can actually do that by doing a basis transformation and then performing a projection. the basis transformation actually turns out to be related to something called a Z2 times Z2 SPT. So it's a symmetry protected topological space. So you do this basis transformation, and then you do this projection. It turns out that these two together project you into the Gauss law, the sector of the local symmetry of the Gauss law. And from the field theory perspective, you can think of it as the following. I have some theory, and maybe I can write it as a partition function. And by doing the gauging, what I'm just doing is I'm adding this Fourier transform term, and then I sum over all the flat connection. And this term here, so the dual model, I can also insert a background gauge field. And this term I have to insert here is exactly the Fourier transform of these two one forms. And this term here is exactly the response of an SPT with Z2 times Z2 symmetry. So this diagram is literally doing gauging. And now to relate it back to that diagram, you just need to note that that formula I told you earlier, if I have a bunch of GHZs of the same color, I can just collapse them into one green dot, which is that one over here. And that one collapses back up into that red dot. So this is why this diagram literally performs the gauging. It takes you between a model with Z2 symmetry and then a model with dual rep Z2 symmetry. Yeah.
Sorry, just to make sure I understand. So if for continuous symmetry, gauging would have involved, the kind of histories of the gauge fields at every time. Here,
By history,
I mean,
that's implemented by this projection here, because this projection here is actually plus. So you're summing over the gauge fields. Sorry, try to say this correct. After the basis transformation, what you're going to implement is you can think of it as the Gauss law. So originally this thing is stabilized by a single x, but after the basis transformation, you can think of it as x. So x on two edges and x on a single vertex. And you can think of this as Gauss's law. It's like divergence of E minus rho. So the two things on the side are fluctuating your gauge field via the electric field. Sorry, fluctuating the vector potential via the electric field, right, which is conjugate to each other. And the other one is turning on and off your matter. Yeah, sorry, I didn't get into the details, but yeah, hopefully you get the idea of how this works. So basically, this basis transformation and the single side projection together, you can think of it as enforcing the Gauss law on each vertex independently, roughly. Okay. So now this is gauging, but notice that if I input a model with Z2 symmetry, my Z2 Ising model, I'm going to output a model with rep Z2 symmetry. They're not related yet. So in order to make them match at the end of the day, what I need to do is I need to now Hadamard, right? And then now do this half shift in order to make it back to the same Hilbert space. So I started with my Ising model with X and ZZ. I did the gauging, and now I get this rep Z2 Ising model on the dual lattice. I need to do Hadamard, so that is now ZZ and X again, and I now need to do this half shift. So in case you're wondering where the translation comes in, this is where it comes in. There's this half shift, which you need to enforce in order to go back from the dual lattice to the original lattice, and you cannot get rid of it. So that is why when you apply Kramers Wannier twice, you get this half shift contribution twice, and that's why there's a full translation on the lattice when you implement it on the lattice. You cannot get rid of it. Okay. So to summarize this part, the idea is we're performing gauging, right? And if we are back to symmetry, the same symmetry, which is related by this Hadamard transformation, we can then do this half shift and relate it back again. So now my goal here is now to try to generalize this picture to a more general setting. Right. Another thing worth noting is that I can make this picture look symmetric if I push Hadamard down through this red one. So now everything here is a GHZ tensor, and it's just connected by Hadamard in the middle. And after this half shift, you can see now that this duality transformation really is symmetric. And it requires the fact that I have this Hadamard so that I can change this red guy back into a green guy. So now this picture is symmetric, and now I have a self-duality up to this translation. And you can also explicitly compute. There are these rules of using these tensor networks, which you can explicitly compute that you get this projector up to this translation.
Can every linear map be written in ZX calculus? There's some.
Every linear map, no. So there is a generalized version of this where instead of a GHD state without a phase, you can have 0, 0, 0 plus e to the I theta 1, 1, 1, for example. And that can actually represent any linear map. For this one, it only can represent things that it only maps X to X and Z to Z. So it's a more restricted set. Yeah, but it's enough for our purposes here. But indeed, people in quantum information, when they want to do this general quantum computing, they actually add this phase back in.
So it's not guaranteed that every kind of non-invertible symmetry could be represented in this way, only this particular kind,
Right,
or
and
is
only
it
for
not-
qubits. Yeah,
only for-
here I'm only doing for qubits, and yeah.
But do you have examples of non-invertible symmetries where we have to go outside this class of
There will be that are beyond this. But what I'm going to focus on today are roughly, you can think of the ones that are gaugeable. So maybe a technical comment is that any anomaly-free symmetry is a representation of a Hopf algebra. And so what I'm going to generalize to is exactly taking this Hopf algebra and using that structure in order to build the corresponding gauging map.
and for some reason, all of those can be represented in this limited class of maps?
Yes. Which I'll get to in a bit. So this will cover all gaugeable symmetries. Well, the symmetries you get from gauging.
Do the topological manipulations of these kind of maps implicitly imply trivialization of F symbols or something like that? Is that where
It's not obvious. Oh, maybe one related comment is that, for example, Shuhang has shown that this operator on the lattice can either flow to Ising or SU2 level 2 in the continuum, depending on which Hamiltonian you have. So there are certain data which is not well defined on the lattice, it's precisely because it's not its own dagger. And so depending on which Hamiltonian, it can either flow to different non-invertible symmetries in the continuum. So that's why the data actually doesn't really match. For example, this Frobenius Schur indicator is not well defined for this operator.
That example means that the translation may or may not act trivially at long distances, so in the continuum, and so therefore you can arise different symmetries.
No, I think in either case, for his example, the translation still acts trivially, but it's just because D is not equal to D dagger, so you cannot relate certain groups to each other. So there's certain data that's not well defined.
Interesting.
Any other questions? Okay. So now I want to talk about the self-duality, going beyond the Ising model. And before that, let me just mention how to do it for the group case first. So actually, a similar map here can be used to gauge a non-abelian group symmetry. So the only difference we need is instead of the GHZ state, this green tensor just needs to copy group elements to two group elements. And instead of addition mod 2, we just need to change this to multiplication. So now this red tensor is doing multiplication. This green is still doing copying. Okay? And the only other ingredient we actually need is a map that takes G to its inverse. I'm going to call this S. People call this the antipode for reasons. And the only difference is, recall in the previous one, I just added the 2 mod 2. But here what we actually want to compute is I want to go, recall that for Kramers Wannier, we want to go from spin variables to the domain variables, right? Meaning we want to compare the difference between two group elements. So on the other side, what we should output is we want to compare these two. So I want to do G2 inverse G3 here, for example. So what I have to do is I need to copy this copy this value, invert it, and then multiply it to the thing coming from the other side. So that's why we need to impose this antipode here, so the inverse. So in the Z2 case, right, this map is trivial, so that's why I didn't draw it earlier. In the general group case, I need this. Okay, so you can see that before gauging, we have a symmetry which is left multiplication by each side. If I multiply every side here by G on the left, you can see that they cancel up there. So it gets killed on the top. And so this side has a left G symmetry, which gets gauged after I push it through this map. Now, what is the symmetry on the other side? What does it look like? This is called a rep G symmetry, but it looks a bit more complicated than the abelian case. In the abelian case, it was just a product poly Z's, if you recall, but now it's more complicated. So instead, for each irrep of the group, what you're going to do is you're going to so what is the thing that gets absorbed when I act from the top? It turns out to be this more complicated operator. What does it do? You copy out each group element, you multiply them all together, and then you compute a character corresponding to some irrep of the group. It can be rep, doesn't need to be irrep. And you notice that since this thing up here is always of the form G1 inverse G2, G2 inverse G3, if you plug that in up here, right, they're all going to cancel pairwise. So this map will act trivially on all states. So you can check that indeed this thing gets absorbed from the top. This operation for a non-abelian group is now non-invertible. And it's because when you multiply two irreps together, right, it decomposes as a sum of other irreps. And for a non-abelian group, you might have more than one outcome here. So you can check that when you multiply two of these symmetries together, it gives you a sum according to this decomposition of irreps here. So for a non-abelian group, this symmetry is non-invertible now. So this map maps you from an invertible G symmetry to a non-invertible rep G symmetry, right? So for non-abelian groups, it does not give us a self-duality. Okay, so gauging non-abelian groups gives us to a dual symmetry, rep G, but it's not the same symmetry, so it cannot give us a self-duality. So how do we get around this? So as I mentioned before, the natural thing turns out to be Hopf algebras. And in fact, in this famous paper by Kitaev, he introduced a lattice gauge theory based on a group algebra. And he just casually mentions, well, one can actually take any finite dimensional Hopf algebra. However, I do not want to make things too complicated. So he knew that 20 years ago, and obviously we're just catching up with him. But that's exactly the right mathematics which needs to be used here to go beyond groups. And let me motivate a bit why this is the natural structure. So I mentioned that for groups, one thing we should have for a symmetry is there should be a notion of multiplying symmetries. And so we need a tensor that, well, multiplies two things together. We also want to be able to split it, meaning if I have a symmetry on one side, but I want to act it on many, many sides, I need to have a notion of splitting it. In the group case, this was just, copying. But in general, this map does not need to copy. It could send one thing to a sum of other things, right? And then it can get more complicated. So we're just going to take this as sort of axioms in some sense, that you have something where you can use to multiply things together, you can use something you can use to split or co-multiply, and these two things should have some compatibility conditions. For example, if I multiply two things and then I split it, it should be equivalent to I each first split them, right? And then I multiply each of them separately. That should give the same answer. For the group case, this is obvious, right? But for a general case, we'll just take this as an axiom that it should satisfy this. And so if you have multiplication and co-multiplication that satisfies this axiom, that's something called a bi-algebra. And then the last thing you would like is some notion of an inverse, or this antipode map I mentioned. And that's given by this axiom. It's telling you that if I copy things, right? Suppose I have G here, I copy it to G and G inverse, and then I multiply them together, that should always give me the group identity. And so it's as if I just eaten this state, and then I forget about it, and then I initialize another identity element, independent of what I ate in here. Yes?
So in the Z2 example you gave, this inverse was trivial, but if you took Zn, it would not be, right?
Yes, it will.
So that Zs would be appearing in the abelian case as well.
Yes, even for the abelian case. Yeah, it's inverting all the group elements. Yeah. Right. So this is the axioms of we're going to take to be called a Hopf algebra. So it just needs to satisfy these properties. Of course, for any group, right, you have group multiplication and copying, they automatically satisfy this. But now there are other things which also satisfy this that are not groups.
Does this allow weak Hopf algebra also, or just?
This is just vanilla Hopf algebra, yeah, which will not give us every symmetry. And that's why I mentioned it will give us only the gaugeable or anomaly free symmetries, turns out. You want this. So this is sort of the full set of rules if you want to ever stare at it. If you go to Wikipedia, it's not written in this form. It's written as some commutative diagrams, which maybe if you're more sort of analytic, you would have an easier time. But for me, I have a very hard time reading those axioms. In diagrammatics, it's all just pictures that, you know, green tensors, the fact of this fusion I mentioned earlier is just, for example, encoding associativity. It doesn't matter whether you glue them together in different ways. And also for this unit axiom, it's just gluing red things into bigger red things, for example. And this bialgebra I already explained, this Hopf, and that the antipode is antilinear. So if you swap, if you invert, right, you swap the order in the multiplication. Yeah, there was a question.
Can you say more about the red node that only has, say, one edge attached to it?
Yes.
Does it instantiate a preferred element of the Hopf algebra?
Yes. In this case, the red is called with one leg is called a unit,
Okay.
which is in the group case just zero. And this green with one edge is the plus state, which turns out to be something called a co-unit. Yeah. Correct. Okay. So, and it turns out that for self-dual Hopf algebras, there's an extra structure similar to that when I said Hadamard swaps red and green, right? If you push through this Hadamard, it changes red to green. With the only subtlety you have to keep track of is that you want this Hadamard to actually square to the antipode. So recall if you did the Fourier transform, right? And you did the Fourier transform twice without the minus sign, what you would do is you would associate x to minus x. And that's sort of the real version of the antipode. You take x to minus x. So what you want to actually have is when you push this through and you push it through twice, what you would actually do is you flip the outcomes because you inverted everything. So that's, you just have, the moral is you just have to keep track of the order of the multiplication. That's all in the more general case, but it's very similar to what I talked about before. So if you have this structure, then now you can use it to construct. For a self-dual Hopf algebra, we have this sort of Hadamard, and we can use it to construct the self-duality operator, very similarly to what I drew before. And it just looks like this, where here I have to have an extra dagger for this Hadamard in the staggering fashion. But this is the operator. And you can compute that each symmetry that gets eaten on this side is something called a rep H symmetry. It's given by, similarly to rep G, I compute the character associated to each irrep of the Hopf algebra, and that's some symmetry. It gets eaten on the left, on the bottom and on the top. And this self-duality symmetry, once I compute D times D dagger, what I get is, I get this rep H symmetry for the regular representation, meaning it decomposes into each irrep, and each irrep appears D times, where D is the dimension of that representation.
What's the arrow mean?
Oh, B, it means it's act from the right. So there's this left-right multiplication, but here it can also be left-right co-multiplication. And for the general case, you need to keep track of whether it's left or right. That's all. Yeah.
Sorry. So in the standard group case,
Yes.
Fourier transform switches the left and the right actions. Left multiplication from the right
I would say
multiplication.
antipode does that. So if I take x to minus G to G inverse, that was flip, right? The left and right.
Yeah, sorry. Yeah,
Yeah.
right. So but here is the antipode doing switching the left and right as well?
Yes, it is. Which means it's in the previous slide, it's swapping the order of the multiplication. I'm not writing this explicitly, but if you take this Hadamard and you squared it, you get antipode. Antipode swaps the order. So pushing this through twice is supposed to be equivalent to pushing antipode through, which is swapping the order. So now that we have this symmetry and we have the self-duality, we can now write down a lattice model. And it turns out you can write down a similar lattice model. We call this the generalized Ising model based on a Hopf algebra, where it has similarly an X term and a ZZ term. And under this dual, so when this term is large, you have a paramagnetic phase, which we can even write down what the wave function is exactly. It's just this green dot for every site over here. You can think of it as an analogy of the plus state. So plus state on every site. And on this side, we have a ferromagnet, which is, you can think of it as like all 0 plus all 1, but now for this Hopf algebra. And when these two terms are equal, you actually get a self-duality, which is enlarged by this operator D, which I wrote down explicitly. And if you restrict to the cyclic group case, this is exactly what covers the clock and the Potts model. So our model is a generalization of the Ising model, the clock and the Potts model, to this non-abelian case, and in particular to this Hopf algebra, where the two sides are mapped by this generalized Kramers Wannier duality.
Is there a statistical mechanics version of this model?
That's a very good point. I'm going to come to it in the outlook in the end. Yeah, but that's an open question.
Towards the end?
Sorry?
No.
Okay. And now, what if the smallest example of a Hopf algebra that is not a group algebra? It turns out the smallest example is an 8-dimensional Hopf algebra called this Kaspar-Yudkin Hopf algebra. It has some weird multiplication, as you can see here. These parts sort of look group-like, but this Z square is very weird. It gives you a sum of things. So that's sort of one indication that it's not a group. You also have to specify the co-multiplication, which I didn't specify here. It's sort of gnarly. But the takeaway is there are actually 5 irreps for this Hopf algebra. And so the paramagnet has 1 state. The ferromagnet actually has a ground state degeneracy of 5 for each irrep of the group. And so, and the Hamiltonian, you can write down an X term and a ZZ term for each irrep. So there are actually 5 ZZ terms, 5 X terms. And interestingly, the point that you were making here is that the ZZ term is not diagonal. So that sort of does not easily allow us to map it to a statistical mechanics model. And the reason this ZZ is not diagonal is because usually we think of a Z as using this copy. For the group, it's always copying, which is why if you input G, it'll output G, and then just copy the value of G out. But now in general, this Z, for a general Hopf algebra, it might give you a sum of things. So this Z might not be diagonal anymore, so it makes the thing more complicated. But it's still interesting that you can still define this generalized Ising model, even though the ZZ term is not diagonal.
You need all to preserve the symmetry.
Right. For us, we just input this Hopf algebra and it outputs us automatically what the ZZ term is, what the X is, what the symmetry is.
J gamma are a bunch of non-zero numbers.
Yeah. This can be something you tune in your phase diagram. That's just a coefficient of each term, how strong it is. So for example, like for the clock and Potts, right, they differ by one term being on or off. So whether you want that term to be there or not. That's a parameter you can tune while preserving the same symmetry. Like you still have Zn, but you can either choose to have Hopf or Potts.
Okay, so
that's tuning that parameter.
You could turn the problematic Z's off, I guess. You could realize the symmetry in a class.
Yeah, you could, but then it just reduces to a familiar group case if you turn on the interesting term off. Yeah. Okay, so we actually did some numerics to look at this phase diagram. And so, for example, there are 5 irreps of the group of this Hopf algebra, and one is 2-dimensional, and 4 of them are 1-dimensional. And so we can first turn off all the 1-dimensional terms. The interesting one is the 2-dimensional one. So let's interpolate between the X term, which is the paramagnet, and the ZZ term, which is for the 2-dimensional irrep. And indeed, the transition should be at 0.5. And what we find is that here we seem to see some evidence of a first-order transition. So now let's turn on the 1-dimensional irreps. And here I'm choosing them to be the same strength for simplicity. And what we seem to be finding is that this first-order transition, if you go up high enough, you go instead into certain intermediate phases with different ground state degeneracies, different patterns of symmetry breaking as you go along the way. They're separated by Ising criticality. And there seems to be some multi-critical point over here, which we haven't been able to determine because our sort of numerics are limited. But it seems to be some theory with quite high central charge, could be around 3. And as far as I know, I don't know a nice model that sort of fits this description yet. So that's sort of still an open problem. We haven't been able to use our numerics to resolve this fine enough to figure out what theory it is.
You're sure it's relativistic?
I do not know. Yeah.
So this funny symmetry is embedded in Ising in some way, in the Ising CFT on the, let's say, the green line.
Sorry, say that again.
Your whole phase diagram has your H8.
Yeah,
symmetry.
this whole thing has H8, and on this self-dual line, you have this extra symmetry.
Okay.
So the only CFT, I guess people really know that has this symmetry is the Ising square CFT. For example, yeah. So that's just C + 1. Oh, maybe I could comment that here, what we're seeing is that we can fit the entanglement entropy, right, to this Cardy formula, and it seems to match pretty nice. But as we scale the system size up, C keeps going up. So it means that we're not, going to a large system size enough for it to saturate yet. That's why our numerics are still inconclusive.
Or it's not log L.
Right. So we also did the infinite version and we also see sort of nonlinear sort of mapping between the entanglement entropy of the half cut and the correlation length. So usually you'd expect a straight line. Right here, it's sort of a bit wavy, so we're a bit unsure what it is.
But I had a more basic question. So this is this H8 symmetry that you're plotting?
Yes, it's the whole phase diagram has a rep H8 symmetry, and then there's an extra symmetry at the self-dual line.
So
self-dual.
So H8 acts in the let's say on the green line that you have an Ising CFT. H8 acts on that.
It might not. It might act faithful.
Okay.
Yeah. So some of it only acts. Yeah. Some of it might not act.
The intuition of why is first order of between the dash one.
That's a good point. So actually, one thing we found only recently is that there's a special point here, which you can call the Potts point. And it's actually, as a Hamiltonian, or as sort of an algebra, actually maps exactly to the 8-state Potts model to some non-local transformation. So actually, we know for sure that this is the first order transition for some point here for 1/2, for example. So there's a special point. So for each Hopf algebra, there's a special point which you can actually call the Potts model in some sense, and it's related to the Haar integral of the Hopf algebra. You want to.
And you're hoping that H8 does act faithfully on your tricritical pair? I guess
that's the hope. Yeah.
Is there a way to just test that by looking at an observable?
Right. I mean, unless you compute spectrum, maybe, and then just act. I don't know a more direct way to check from numerics.
Maybe correlation functions, seeing that they.
Which part does not act faithfully?
For example, this Ising, or here, like
the duality defect. So the duality defect maps different points of the phase diagram.
Yes.
Right?
Yes. Oh no. The duality defect is the extension of rep H8. So rep H8 acts everywhere.
Rep H8 acts everywhere at any point. Here.
Yes, and the duality reflects this diagram.
So but then that one is acting everywhere, right? So I'm a bit confused about the comment that something doesn't act. Does the square of the duality defect contains all these?
He was asking about how does rep H8 act on the single Ising? And what happens is not acting faithfully.
But the duality defect acts there because it moves.
It will move it to there.
Moves it there, and the square of the duality defect contains everything.
Contains everything, so it'll map. So it'll be a projector into the symmetric subsector, but it might not act faithfully on, say, the ground state or other states.
So all states are deformed under it.
So for example, it's faithful here because it's the whole rep HA is broken. Right? So they're all permuted into each other by the action.
But you say that in that Ising place, there are some of these HA symmetries that are not acting on any state at all, or just on the ground state?
I think not any state at all, but I should double check. And I don't remember which one acts non-faithfully off the top of my head. Okay, so let me conclude. So today I talked about dualities in quantum mechanics and generalized them to dualities in quantum many-body systems, right? And I tried to convey the message that dualities can map between these phases of matter, but some information is lost in the process. So that makes these dualities non-invertible. But it's still interesting because if it leaves a system invariant, then it can become a non-invertible symmetry. This simplest example is the Kramers Wannier duality. And I showed how we can formulate this duality as a map precisely using these simple tensor network diagrams, just using GHZ tensors and the Hadamard. We can string together this operator, which maps X to ZZ over here. And going beyond Z2, I showed how to generalize beyond the Ising model, clock, or Potts model, beyond abelian groups, right? And we need to go to Hopf algebras to go beyond to non-abelian groups. So there, I only studied one phase diagram, but of course there are an infinite family of phase diagrams to explore. There are an infinite self-dual Hopf algebras, it turns out. So many more to explore and potentially interesting quantum critical points. And an interesting question is whether they have a classical static counterpart. I mentioned because this ZZ term is diagonal. For these Hopf algebras, there's not a natural basis for example, for the group algebra, you can say the natural basis is the group elements, but for a Hopf algebra, there's no natural basis. And so whether you can make the Hamiltonian stochastic, meaning you only have positive coefficients in the off-diagonal terms, is not obvious. It depends on the basis, and I don't know whether there is a classical static counterpart. I mean, but nevertheless, there still could be ways that one might be able to simulate them using quantum Monte Carlo. Not having a stochastic Hamiltonian actually is sufficient, but not necessary for doing quantum Monte Carlo simulations. So it could be interesting whether we can still do that despite not having an analogous classical static model. So let me conclude here and thank you for your time.
Sorry, can you show the tensor network that you had for the Hopf algebra where you have the dagger?
Yes.
That one. Can you say a few more words? So previously you had the red squares up there, so I imagine that was using the Hadamards.
Yes.
Right? But now that dagger thing, can you say a few more words about it?
It was because I had an antipode for the general gauging. I had an antipode here, and it's due to the fact that Hadamard square is the antipode. So when you this is the too far. Yeah, there's an antipode here. So if I put a Hadamard up there and I push it down, right, you're going to get two Hadamards, but one Hadamard times antipode is going to be Hadamard dagger.
I guess my question is that there are two operations that send G to G minus one. One is the antipode, the other one is the dagger or star operation.
Yes.
Algebraically, you call it star operation.
Yeah. For the Hopf algebra, they're also distinct. And here I'm doing the antipode. There's also a separate star operation that might not act.
So your dagger is not this star.
No, there's a separate star operation. We usually don't really think of it at all when we think about groups, and there was a huge headache for me. I was like, oh, I've been conflating the two for a really very long time, but yeah.
Thank you.
Yes.
Can you comment on the applications of non-Clifford algebra for the self-duality?
Well, for the Z2 case, this is a perfectly Clifford operation. It maps polys to polys, right? But unfortunately, I don't think we have a nice notion of Clifford for non-abelian groups, as far as I know. So I don't know what a nice notion of that is. Well, you can say it maps X to Z, it maps X type to Z type, but I guess that's as much as you can say. It's not that we have a Clifford hierarchy for non-abelian groups.
For like say like rep G symmetric Ising models, you can get the case where like the symmetry broken ground states have like richer structure. They might be an MPS, and the symmetry action could even say like mix them. In the model here, are the symmetry broken grounds, so are they just like product states and just permuted, or do they also have?
They are. I have it here. So in this phase diagram picture. So this is the MPS of the ferromagnet.
Right.
And well, this is a particular state, but you can break it down into each cat state. And each cat state is labeled by an arrow. So one way you can actually write it is it's just you take the representation and then you sort of glue them together like this. That's the MPS for each ground state. So if the bond if the dimension of the irrep is 1, it factors into product state. But if not, it becomes an MPS with the bond dimension is that dimension.
In the case of Potts models clock models or multiple clock models, you could find points that are not duality invariant, but triality or n-ality, or have a higher order notion of invariance that's not order 2. Is there something like that for a general Hopf algebra? Have a triality invariant?
I guess, for example, are you thinking of like the Ashkin-Teller model, Z2 times Z2 when you have some triality?
For instance, that's like the simplest one.
Yeah, so
that does imply an additional symmetry.
Right, that's sort of some enlarged symmetry. Right, so one related thing we're trying to look at is related to this notion of a Potts. So you can think of the Z2 times Z2 at the Ashkin-Teller point is equivalent to the 4-state Potts. And that turns out it's because both of them are at the Hopf point of this, at the Potts point. There's this particular Potts point related to, you can pick these, related to these coefficients. So there's a special coefficient here related to the Haar integral of the Hopf algebra, which tunes you to a special point with a larger symmetry. So we're currently looking into that also to see what is the enlarged symmetry for these specific models.
But the notion of a self-dual Hopf algebra, like the duality action of Hopf algebra, does not have a natural order n generalization.
I mean, for this triality in the Ashkin-Teller, I think it's you can think of it as adding an SPT and gauging, right? For example, and you're combining sort of the gauging with other operators. So you can start with this duality, but in addition, add extra symmetries, and then those two together, they form a larger group, which might give, these trialities. So I guess you can sort of view it as related to that. So you have to find these larger symmetries and combine them with Kramers Wannier in an appropriate way.
Let's say that.
Wow.